Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
Reservoir engineers generally have precious little information about the mass of rocks and fluids that they must characterize. Often they must predict the behavior of millions of cubic feet of reservoir fluids based on measurements made over a few points in time. Every technique that allows them to investigate more fully the volume of reservoir fluids is a valuable engineering tool. As we have said elsewhere in the 400 series on well sampling and testing, one approach to this problem is to see how the whole reservoir, or at least some relatively large portion of the reservoir surrounding a well, responds to a pressure disturbance. As the reservoir adjusts to the disturbance, we measure the response and compare it to an expected response predicted by a mathematical model of the reservoir's behavior.
The most convenient way to disturb a reservoir in a controlled manner is by suddenly producing or suddenly shutting in a well. The reservoir's response to this disturbance, a fluctuation in pressure, is easily measurable as a function of time, most commonly at the point of disturbance. The analysis of this pressure data, referred to as pressure transient analysis, can greatly expand our knowledge of the reservoir, as seen through the wellbore window. Typically, the reservoir data that can be obtained from a pressure transient analysis include reservoir pressure, permeability, skin factor, the damage ratio, the PI or productivity index, radius of investigation and time to stabilization, degree of reservoir depletion, and the presence of faults, barriers, fluid contacts, or pinch-outs.
In this module on oil well testing, we shall begin with a review of the theory upon which pressure transient analysis is based. We shall then apply this approach to data from 3 reservoir systems. First, a reservoir which acts as a homogeneous system. Next, a hydraulically fractured well, and finally, a dual porosity system. Let's begin.
The basic model for describing reservoir pressure response to flow is developed by combining 3 fundamental equations. A mass balance or continuity equation, which states that the rate of accumulation of mass in an incremental element is equal to the rate of mass flux into the element minus the rate of mass flux out of the element. A transport equation, in this case Darcy's law, which describes the relationship between volumetric flow rate and the pressure gradient, and an equation of state, which relates fluid density to pressure and temperature. By combining these equations and making some assumptions regarding the system, we can derive the radial diffusivity equation, a partial differential equation relating the rate of change of pressure with radial distance and time. Solving this equation for certain conditions allows us to develop a method for calculating reservoir parameters from measurement of the response to pressure disturbances in the reservoir.
In the other programs of the 400 series, we have spoken at greater length about the use of these flow equations in both conventional and modern methods of well test analysis and interpretation of pressure time data. Here we'll just review briefly. If you are unfamiliar with the basic concepts and techniques of each method, be sure to view the other programs before continuing.
Let us begin by making the first of many assumptions concerning our reservoir model. First, the reservoir is horizontal and of constant thickness, and is of infinite radial extent. It is bounded on top and bottom by impermeable boundaries, and is homogeneous and isotropic. Next, the producing wellbore is completely open to flow over the entire reservoir thickness. Next, only a single phase flows in the reservoir. And finally, the reservoir fluid is slightly compressible and at a constant temperature. Our model must also describe all the conditions existing in the reservoir, the inner boundary conditions at or near the wellbore itself, the conditions away from the wellbore, essentially the reservoir itself, and finally the conditions at the outer reservoir boundaries. When a well is produced after a period of being shut in, A simple Cartesian plot of pressure versus time reveals a succession of 3 flow periods. A well-bore influence flow period, also known as the transient flow period. During this flow period, the reservoir acts as though it were infinite in extent. A transitional flow period. Normally, no analysis is made of this period, owing to the complex interactions between the changing reservoir pressure and the reservoir geometry. And finally, a steady-state or pseudo-steady-state flow period. Due to the difficulty of maintaining a constant flow rate during a drawdown test, emphasis has been given to the development of methods to analyze buildup data. The Horner method of pressure buildup analysis is based on the assumption of a constant rate of production prior to the test, beginning from a uniform initial pressure in an infinite reservoir. The graphical form of Horner's method will yield a straight line on a semi-log plot of pressure versus time. In actuality, Horner plots usually show deviations from the expected straight line during the early time portions of the build-up plot, largely due to the effects of well-bore damage, multi-phase flow, and well-bore storage effects. These early time effects are usually overcome in later time. Thus, the straight line can ultimately be extrapolated to determine the average reservoir pressure. Additionally, from the Horner analysis results, we are able to calculate the permeability, flow capacity, and skin factor.
The chief limitation to the Horner method is that it is only valid after wellbore storage effects have ended and before the boundary effects have begun. If wellbore storage occurs over the entire duration of the test, or if boundary effects begin immediately after the wellbore storage effects, it will be impossible to obtain the necessary straight line on the semi-log plot, and thus the Horner method will be inapplicable. With the modern methods, the presence of wellbore storage or boundary effects does not pose the same problem to the analyst. As we've said elsewhere in the 400 series, the modern methods of well testing make use of all the data acquired during the course of a well test, including the data from early time.
Modern methods graphically characterize the data by plotting it in the form of delta P, the change in pressure at the sand face, versus delta T, the elapsed test time, in log-log form. Additionally, the pressure derivative, with respect to time, is also computed and plotted on the same log-log plot. More about this momentarily.
Right now, let's look at the significance of the various sections of the curve depicted on the log-log plot. This will prepare the analyst to undertake a qualitative analysis of the test data and to indicate the point in time when a particular flow regime has ended and another begun.
For example, here's the beginning of the wellbore storage influence period, as evidenced by a line of unit slope, which can be drawn through the early time data. Following the wellbore storage influence period is the infinite acting period, evidenced on the log-log plot by the straight line portion of the data curve. The boundary influence period is evidenced by a deviation from the infinite acting period. However, the boundary influence period may be undetectable on the data plot. It may only be evident on the derivative plot. The derivative plot is determined with respect to the superposition time function. Basically, the plot is made by calculating the speed at which pressures are changing during the transient. Generally, the derivative plot is calculated on a computer. There are several methods and choices available for computing and smoothing the derivative values, and it should be noted that any measurement errors made when conducting the test can contribute to creating a noisy derivative. The derivative plot is especially useful when trying to determine the end of the wellbore influence period. Note the characteristic hump in the derivative values, followed by a flattening. The end of wellbore storage is sometimes evident on the data plot as well, but it can be more readily and accurately seen on the derivative plot. The horizontal portion of the plot, where there is no change in the derivative, is indicative of the infinite acting radial flow period, and hence that section of the pressure transient which would produce a straight line if plotted on semi-log paper. The boundary influence period can be recognized by a late time deviation of the derivative value. As before, the presence of a boundary may not be evident in the data plot at all. In this specific example, the data plot remains virtually unchanged while the derivative plot bends upward. Ultimately, the specific shape of this section of the derivative curve can be used to determine the type of boundary that is influencing pressure behavior. For example, no-flow barriers or constant pressure boundaries.
The derivative plot is also helpful for determining the cause of an anomalous pressure response, although this particular topic is beyond the scope of this video. There are, however, SPE monographs and other technical publications that provide much useful information on the analysis of anomalous pressure situations. Let's summarize the material covered so far. In the first unit, we mentioned the basis for well test analysis and interpretation. We spoke of three necessary equations: a continuity equation, a transport equation, and an equation of state to derive the diffusivity equation, the basis of pressure transient analysis. We spoke also about the two methods, the conventional and the modern, and the way that each approach treats the pressure in time data. Lastly, we spoke of the derivative curve and its usefulness in providing interpretive information beyond what is available from a typical log-log plot of the data. In the next unit, we will speak even more specifically about the uses of these methods in actual tests run on wells. At this time, please stop the tape, read over the supporting material in the manual, and work the exercises. In the last unit, we did not discuss type curves and type curve matching. We will be spending some time with them in this unit, so if you are not familiar with the basics, please view both PE 401 and PE 404. Here, we'll provide simply a brief review.
A type curve is generally a log-log plot of pressure versus time expressed dimensionlessly, that is, prepared in such a way that the curves are universally applicable for all types of specific reservoir environments. One set of curves for wells with wellbore storage and skin in a reservoir with homogeneous behavior, another set of curves for a vertically fractured well in the center of a closed system with no wellbore storage, with fractures of infinite conductivity, and so on. The procedure for utilizing the type curves is quite straightforward, especially if we make use of the software currently available for pressure transient analysis. Place the log-log plot, including both the data curve and the derivative curve, on top of the type curve, and move the log-log plot over the type curve until a match is obtained. We thereby obtain values for P sub D and T sub D, as well as a value for C sub D e to the 2s. These values will then be used to calculate values for permeability and skin for the reservoir. When the proper match is obtained, the pressure and derivative data will lie on the corresponding curves at the same time. If the best match lies somewhere between the type curves, not to worry. The computer will generate a unique type curve for both data and derivative curves.
Ultimately, the values obtained from a type curve analysis should show close correspondence with the values obtained from the conventional Horner analysis. With this information on both the Horner and the type curve methods of pressure transient analysis in hand, let's now look at a build-up test, specifically the final flow period of a drill stem test conducted on a well in the North Sea. This test was run in order to determine current reservoir pressure and to calculate reservoir parameters previously estimated from well logs.
The following information was available prior to the test. The estimated initial pressure obtained from the initial shut-in period is 7,500 psi. The formation thickness is 18 feet. Fluid compressibility is 15.4 times 10 to the minus 6. The formation volume factor is 1.22. Viscosity is 0.53 centipoise. Porosity 15%. Wellbore radius 0.4 feet. The well was produced at a rate of 674 barrels per day. We first construct a simple Cartesian plot to check for the presence of any anomalous tool response. The tool seems to have worked properly. We next construct the log-log data plot. We note the presence of wellbore storage as indicated by the unit slope of the early time data. Next, we display the values of the derivative. The derivative curve displays the hump characteristic of wellbore storage. Following the wellbore storage influence period, the derivative values appear to stabilize at an elapsed time of 0.1 through 0.35 hours, indicating the infinite acting radial flow period. The short duration of the radial flow period, followed by a steady increase in the derivative values throughout the rest of the test, suggest either severe wellbore damage or the presence of a near wellbore boundary. Let's now begin the actual match of the pressure and derivative data using the appropriate type curve. As previously, we move the log-log plot over the curves until a suitable match is obtained for both the pressure and derivative data, here. From this visual match for a delta T value of 1 and a delta P value of 100, the corresponding values of T sub D and P sub D are 0.94 and 220, respectively. Also from the match, we obtain a value for C sub D e to the 2s of 1.4 times 10 to the 23rd. Now, using our value for P sub D, we calculate a value for the permeability, 32 millidarcies. Using a value of 200 for C sub D, we obtain a value of plus 24 for the skin factor. This is very high.
Let's now turn to the Horner analysis and compare the results obtained from this method with those obtained from type curve analysis methods.
From our derivative plot, we see that infinite acting radial flow occurred following an elapsed time of 0.1 hours, which corresponds to a Horner time of 134 hours. Therefore, the correct slope on the Horner plot begins after this time and yields a slope of 60.5 psi per cycle. Using Horner techniques, we obtain a permeability of 32 millidarcies and a skin factor of plus 25, values which correspond closely to those from the type curve analysis.
From this information, it appears that the steady increase in the value of the derivative discussed earlier could be due to significant near wellbore damage. The magnitude of the damage certainly appears to justify some form of remedial work, perhaps a matrix acid job, but first the engineer should determine the possible cause of this damage. That completes our qualitative and quantitative analysis of a fairly simple reservoir environment. There are some details which have not been presented. Fortunately, much of it is covered in the PE 403 manual or elsewhere in the 400 series on well testing. Specific details on pressure transient analysis is presented, as we said earlier, in the SPE monographs and other technical publications. Let's now take a look at a more complicated situation, a build-up test in a hydraulically fractured well.
Hydraulic fracturing has become an increasingly common practice for improving the productivity of low permeability reservoirs and mature reservoirs. The purpose for testing fractured wells is to determine both fracture and reservoir properties in order to evaluate the success of the fracture treatment and to predict the long-term deliverability of the reservoir. A well is hydraulically fractured by pumping a fluid and proppant under high pressure into the formation until the rock cracks. The formation rock closes on top of the proppant, leaving a new pathway through which well fluids will flow, thereby improving the productivity of the well. Fractures are not easy to model analytically, since the conventional analysis of pressure transient data is based upon theory and procedures that assume, among other things, that the formation is homogeneous with constant permeability and porosity, and that fluid flow in the vicinity of the wellbore is radial. Obviously, any reservoir heterogeneities, and this includes fractures, will cause the pressure behavior of the well to deviate from the behavior predicted by conventional pressure transient analysis methods. And so we need to find out just how the pressure behaves in a hydraulically fractured well in order to avoid seriously misinterpreting the pressure transient data. We need to make some assumptions about the fracture itself. We assume it is a vertical fracture, the same height as the reservoir, extending outward from the wellbore. Other types of fractures are possible, however. Let W be the fracture width, H the fracture height, and X sub F the fracture half-length. After a well has been fractured, a new set of flow regimes arises, different from the flow regimes prior to fracturing. These new regimes are fracture linear flow, where flow into the wellbore is contributed exclusively by the fracture, not the formation. Bilinear flow, in which fluids entering the wellbore come from both the fracture and the formation. Formation linear flow, in which the formation flows linearly into the fracture. And finally, pseudo-radial flow, in which the presence of a fracture is undetectable in the data. Fracture linear flow normally occurs during the same early time as wellbore storage effects, and thus is often invisible in the data. The presence of bilinear flow is evidenced in the data by a straight line of 1/4 slope on the log-log plot. Formation linear flow is recognized by a line of 1/2 slope on the log-log plot.
The start of pseudo-radial flow may occur at a time that is economically impossible to reach in the course of the test, and it is very dependent upon fracture penetration. For shorter fractures, pseudo-radial flow may develop earlier in the test. However, as fracture length approaches the drainage radius of the well, pseudo-radial flow will develop later, if at all. In this case, an analysis of data according to conventional methods may be impossible, since the equation will contain two unknown variables, permeability and fracture length. In such cases, it is imperative that a pre-frac evaluation be run in order to estimate a value for the permeability.
The success or failure of the fracture treatment can be determined using the calculated skin factor. As a rule of thumb, the frac treatment is successful if the skin is reduced to less than -3. If wellbore storage effects last for a significant period of time, it is possible that the first 3 flow regimes will be obscured by its effects. If this occurs, there is no remedy. Analysis by conventional methods to determine fracture length is impossible. If the wellbore storage effects are not significant, a bilinear flow analysis or a linear flow analysis may be undertaken to determine fracture length if the data support these regimes. For example, from measurement of the slope of the line on the tandem square root plot, fracture half-length x sub f can be determined, provided that we have on hand an estimate of the permeability value. Once pseudo-radial flow has been achieved, conventional methods can be used to determine KH.
The conventional method often cannot be used to determine the permeability, skin factor, and fracture length for a reservoir. Let's now look at an actual example of a buildup test conducted on a hydraulically fractured well and see how the combination of conventional and modern methods can be used together to analyze the reservoir system. The test data is given in SI units.
We are given the following data on our hydraulically fractured well. An initial reservoir pressure of 25,990 kilopascals, a formation thickness H of 25 meters, a total compressibility of 3.05 times 10 to the minus 6 per kilopascal, a formation volume factor of 1.26, a fluid viscosity of 0.65 centipoise, a porosity of 12%, and a wellbore radius of 0.086 meters. The test duration was 240 hours, preceded by a producing time of 7,800 hours. We are asked to obtain values for the reservoir flow capacity, the permeability, the fracture half-length, the skin factor, and the flow efficiency. We see here a Cartesian plot of the pressure versus time data. Ordinarily, this plot is not of great significance. We generate it to be sure that the data is free from the effects of erratic downhole tool performance. No irregularities here. The tool seems to have worked properly. Next, the log-log data plot is generated. We note that the unit slope characteristic of wellbore storage is not evidenced. This could be due to the fact that no data was recorded for earlier than 0.0833 hours, about 5 minutes, in the test. If wellbore storage did occur during this early time, it is not evident. The derivative plot is next. The characteristic hump in the plot indicative of wellbore storage is likewise absent, confirming that the early time data during wellbore storage was not recorded or that wellbore storage did not exist. We note the presence of half slope, indicating formation linear flow, which should be followed by pseudo-radial flow. The derivative plot supports this conclusion as evidenced by a flattening occurring at the same time. For our Horner analysis, we utilize the specific data points from the log-log plot, which indicate the presence of pseudo-radial flow. Here we define them by using the cursor to create a box, and then instruct the computer to generate the Horner straight line. We see the solutions obtained using the Horner analysis methods: an effective permeability of 7.16 millidarcies, a skin factor of -5.5, and a flow efficiency of 2.32. Note that we are unable to obtain a value of x sub f, the fracture half-length, using the Horner method. To determine x sub f, we replot the data on the tandem square root plot. Pressure is plotted linearly on the vertical axis. The square root of T sub P plus delta T minus the square root of delta T is plotted on the horizontal. We then select a portion of the data from the linear flow period, and from its slope calculate a value of x sub f equal to 41 meters, completing our analysis of this hydraulically fractured well according to conventional methods.
The next part of the well analysis will be undertaken using type curve matching methods. We'll then compare these results with those obtained from the Horner approach.
Again, we see our data plotted in the form of log delta P versus log delta T. We select the appropriate type curve for our vertically fractured well, overlay our data plot upon it, and move it until we are satisfied that our match is correct. Note as before that the values of delta P and delta T, which are read directly off the log-log plot in the curve matching process, are not presented here, only the data points. The computer does all the record keeping for us. Having made the match, we obtain the corresponding values for P sub D and T sub D. At this point, we can now solve for K and X sub F using the appropriate equations. To determine permeability, the pressure match point of delta P equal to 690 kilopascals and a corresponding P sub D of 1.22 were read directly from our log-log data plot and type curve. Using this equation, we then solve for a permeability of 7.21 millidarcies. To determine the fracture half-length X sub F, the time match points are utilized. From our curve match of delta T equal to 1.0, T sub D equals 0.068. Fracture half-length is calculated from this equation. Our final solution gives X sub F equal to 40 meters. The skin factor can be calculated from this equation. Substituting the appropriate values, we obtain a value of minus 5.46 for skin. Our final solutions obtained from the type curve matching method show a close correspondence with those from the Horner approach.
From the preceding analysis, we can conclude that the frac job resulted in an improved skin factor and an improved productivity from this relatively low permeability reservoir. The fracture lengths calculated from the test data compares favorably with the frac lengths calculated from fracture growth models. You can also view PE 305 for more information on the specifics of fracture stimulation. Now, let's take a look at another test of a non-homogeneous system. In this case, previous reservoir work suggests that this reservoir could be a dual porosity system. Generally, a dual porosity system is thought to consist of natural fractures and the rock matrix.
The following reservoir data is available: a formation thickness of 7 feet, a compressibility of 2 times 10 to the minus 5 per psi, a formation volume factor of 1.5, a viscosity of 0.3 centipoise, a porosity of 5%, a wellbore radius of 0.29 feet, and a flow rate of 830 barrels per day. Again, our Cartesian plot shows no evidence of erratic tool performance during the test. The presence of 2 parallel lines on the semi-log plot is a strong indicator of dual porosity, although without additional evidence, other interpretations would be possible. Our subsequent analysis of the derivative plot will determine if the slope of the line on the semi-log plot here can be used to specify the presence of radial flow, from which we can calculate KH. Based on the strong indications of dual porosity, our next step is to generate the data and derivative curves and overlay them on a set of dual porosity type curves. We seek the best match. Here, note that the data plot deviates from a greater to a lesser value of C sub D e to the 2s, again a strong indicator of dual porosity. The most defining characteristic of dual porosity is to be found on the derivative plot, the trough, here. After wellbore storage effects have ended, the curve indicates 3 flow periods. First, a period during which flow to the wellbore is contributed exclusively by the Fisher system. Next, a period of transitional flow behavior. And last, a total system flow period, during which flow into the wellbore is contributed by both Fisher and matrix systems. Using values determined from our type curve match, we are able to determine a value for the total system KH. From the curve match for a delta P of 10, we obtain a P sub D match point of 0.6. Incorporating this value into our equation for KH, we obtain a value of 3,164 millidarcy feet, or for a formation thickness of 7 feet, a permeability of 452 millidarcies. To calculate a value for the skin factor, we must first solve for C, the wellbore storage coefficient. To do this, we use the time match points. For a delta T of 1.0, we obtain a T sub D over C sub D of 160. Substituting the remaining values, we obtain C equal to 0.019 barrels per PSI. With this value, we calculate the dimensionless wellbore storage constant for the total system, fissure and matrix, using this equation. With this value, we finally calculate a value of skin using this equation. We obtain a value of minus 4.1 for the skin factor. To characterize the heterogeneity of this system, we make use of the developments of Warren and Root, which utilize two terms: omega, the ratio of the storativity of the fissure system to the storativity of the total system, and lambda, the interporosity flow coefficient, which determines how quickly the matrix blocks start to contribute to flow. For homogeneous systems, omega will equal 1.0 and lambda will equal 0. Essentially, lambda governs the depth of the trough on the derivative plot and defines how the transition is made between fissure flow and total system flow. These terms are not essential to the determination of KH or skin. However, if a suitable match was not obtained, reservoir modeling to obtain a better match could be undertaken using these terms as shown here. This may result in more accurate values for skin and permeability.
Let's begin to summarize. In this second unit, we began with a brief review of type curves and a practical example of a build-up test from a reservoir with few anomalies. We performed our analysis of the well data according to both conventional and modern methods. We then moved on to a discussion and analysis of pressure transient data from a hydraulically fractured well, and finally, an analysis of data from a dual porosity system. As you saw in the case of the hydraulically fractured well and the dual porosity system, the procedures become a little more complicated. Both methods of analysis, the conventional and the modern, are usually applied to the same test data as a means of comparing and verifying results and to avoid errors of misinterpretation. Certainly the challenge ahead is to apply these methods to some of the more heterogeneous reservoir systems throughout the world. For now, please work the exercises in your manual. Good luck with your efforts in well testing.